Thank you very much. Well, first of all, thank you for the invitation to give this talk. For me, it's quite satisfactory to come back to the university some years after I leave this faculty. So you can imagine I graduated a long time ago. So I have maintained the same title for the talk, but I am going to give you a more general talk because I thought this was intended at first to present a specific work, but you clarify me afterwards that this is more like giving an overview of what we are doing in terms of the whole work of the doctoral. So this is just a part of what I am going to talk about, the algorithm that we have developed to calculate these periodic solutions. But I want to talk more generally of what we are working on, what are the different works we are doing in parallel. Some of them, they are not close, of course. This is additional work, but I have to say that I am the fourth year student now. So hopefully this year, the next year, I should be presenting the PhD talk. So what are we doing? Well, we are working on problems on traffic dynamics. And traffic in a general sense. Traffic, we refer to road traffic, to transit traffic, but also telecom traffic. What we're trying to do is to come together or to put together the different dynamics involved in problems that mix different dynamics on the movement of, for example, vehicles and on the transmission of information that is used to control this movement of the vehicles. Okay. Also relevant is the network structure. The network structure is also important because it depends on how the network is built up. For instance, in a mobile network, whether you base your communications on base stations or you are doing some kind of broadcast between the vehicles. Okay. So this is what we are intending. Right now, generally, these kind of problems, these dynamics are studied apart. And what we want to see is what happens when you study these kind of dynamics all together. And very specifically, the communications and the mobility dynamics. This is an example. Probably you can see it very well, but this is a road traffic which is controlled, or the vehicles are autonomous driven, and the information that is used to control this the movement is exchanged via some messages broadcasted using some technology. We are going to speak later on this technology. Probably some of you are very aware of these technologies right now in 5G. But this is the general set of the problem. So the road traffic is normally normally modeled as a system of interacting particles. And well, this is something that has been done during the last century for a long time, and there are many models. I am going to introduce them very briefly. The change now is that this is being now affected also for the telecom technologies that are normally called V2X, vehicle to everything technologies in 4G and 5G. Okay, so the road traffic, how is the road traffic model? Or how has it been modeled traditionally? There are two kinds of models. One is the microscopic model, in which the traffic is seen as individual particles. There is, you study what happens to one vehicle in respect to what is this vehicle or the driver is seen in the surrounding area, and very particularly what is happening with the vehicle just in front of this vehicle. The most usual models that are used are the car following models, where the acceleration of a vehicle is dependent on the distance with the vehicle in front of it, and also the relative velocity and some other variables, varying variables. The other types of models are the macroscopic models, in which the traffic process is seen as a fluid. And for this, the well-known equations for modeling fluids, the continuity equation and the momentum equation, the PDEs, these PDEs are used. Okay, what is done or what is difficult in this kind of problems is to determine what kind of momentum equation to use, depending on what are the dynamics that are driving the vehicles. Okay, so going to what is the title of the talk, one part of the work was focused on one specific microscopic model, a car-following model that is following a specific law that has been proposed by my thesis advisor. And well, there are more simpler models than this one, but the other models lack some of the adaptability or realistic characteristic that this model has. I can go to the details of the model. The model says that this g, which is the acceleration of this following vehicle, is dependent on the space between the vehicles and on the relative velocity of the vehicles. And this is a complex expression, so that to have, as I said, a realistic behavior from the following vehicle. What is relevant here, very relevant, is this kind of models normally are retarded models. This means that we have some delay in the time variable in the reaction of the driver or the vehicle with respect to when the measurements of the variables are measured. Okay, this is very important because delay equations like this one, this is a delay differential equation, and there's also a lot of theory behind this. This kind of equation presents a phenomenon which is called the Hopf bifurcation. For those who are not familiar with this, Hopf bifurcation is when you are in a dynamical system, you are in a non-linear dynamical system, you are in a situation of equilibrium, and even when the system is delayed, you reach an equilibrium, a constant equilibrium. Like in this, here in the left-hand side, you can see two graphs for the space and the relative velocity between the two vehicles, how they evolve from these initial conditions. And you reach this constant equilibrium in which you start in a situation, you go nearer and nearer, and you then continue with the same distance. But and this is for values of delay that normally are low, or starting from zero up to a specific delay. In this case, the limiting delay is 1.3 seconds for this model. And starting from this delay, the behavior is different. The behavior is that you start approaching, and then you oscillate, and you keep oscillating during all the movement process. Okay, this is this situation. So this is an explanation, or one of the explanations behind the formation of waves in traffic situations and strange behaviors or non-stable behaviors in specific traffic conditions. Okay, so what we have done and we have worked on is in deriving the explicit expressions for these periodic functions here. Okay, because to have these functions or this behavior, or to characterize it, you normally use numerical integration through Hecuta methods, this kind of methods, or low order approximation. There are some methods that provide this solution for these kind of systems, but normally you have solutions up to second, third order at most. What we have done is generalize existing methods, in particular the Poincaré method, based on a prior work from another teacher from the Universidad Politécnica, Alfonso Casal. And well, I can't go to the details, as you can imagine. What we do what is done in this method is to normalize the initial equations, to change variables, the time, the dependent and independent variables, so that you have a standard form of the equation that is always solvable with 2 pi solutions, periodic solutions. And you search for solutions in the form of series expansions. This is a scheme of what you do with that, with all that. This is really complex behind the scenes, because you have to do at the same time numerical and symbolic computations. To do this, we have used Maple of course, because you end up with really huge equations, so that you have to integrate and to vectorial products, scalar products, these kind of things. But what you do at the end of the day is a series expansion that is at the same time a kind of Taylor or exponential series expansion in terms of these individual functions. This is a 1, zeros is a 1, and these individual functions is a kind of truncated Fourier series. So you build up at the same time, you build in this direction, and at the same time in this direction, you are building a series expansion and a Fourier series expansion. Okay, so that you see what kind of solution we end up with. Okay, it's a truncated Fourier series. So to check how this behaves, well, I'm going to show you some results. This is for the model that I have shown at the beginning, and this is for a delay of 1.4, as you recall, is 1.3 the limit. So here we have some oscillations. Well, this is for the different orders of what happens if I take just the first term of the series expansion, the second, the third, the fourth, and how this is converted to the final solution. Okay, and this is the comparison with a numerical integration. This which is solved with MATLAB. This is obtained with MATLAB, and this is obtained with our method. Okay, this is for a greater delay, 1.6. If you see the solution, when you increase the delay, the solution gets higher in amplitude and longer the period of the solution. Okay, and this is for the third delay for 1.8, which with 8, as you can see, with 8 terms in the series expansion is not enough. Here we have some differences with the more exact solution of the numerical integration. But eventually, if you keep creating more terms, we have been able to compute this up to order 20 in a standard computer, which is more than enough to have a very accurate solution. The advantage, this has some advantages. Probably the most important is you can pre-compute the coefficients for this series expansion, and you can, in a specific problem in which you don't know the delay that you're going to have, you can check what is the behavior of the system and not rely on a numerical integration that sometimes takes too much time, and it is slow in convergence to the final periodic solution. Okay, so this is one part of the doctoral work. This is the object of one paper. We are in the process of publish right now, but I want to speak some more on some other things that we're doing. I think they're interesting. Going to the macroscopic view, that is like a flow with the flow equations. There is a process to convert the traffic process seen as a microscopic process that we have just seen into the macroscopic view. And this is done through averaging functions like this one. This can have any of these shapes. It's symmetrical, positive, and with a maximum in the 0 point. And this is symmetrical in the time and in the space. Okay, I have not said this at the beginning, but the space that we are considering so far is just a single length. Okay, so we are just in one dimension in space. So from this microscopic field equation, we create with some Dirac deltas representing the position of the different vehicles, and the flow represented by the velocity of each vehicle multiplied by the Dirac delta. Well, you start to do this kind of averaging process by integrating with this averaging function. well, after many manipulations, this is also something quite involved, and but I don't. Anybody interested in the details behind all this, please ask me. I can provide. Okay. What we are able to do is first to create with this process the continuity equation in terms of the partial derivatives. This is the same equation that I have shown before. This is the continuity equation in the abbreviated form with the subindexes. And this is the momentum equation, the other equation that we end up also after a quite involved process in this expression that, as you can see, have here an average of the acceleration, the individual acceleration. This average of the individual acceleration, is the one that we are using in the microscopic view. But there is a problem. In the microscopic view, normally we are considering some delay, so we need to make some kind of linear approximation to this acceleration based on this delay. This is extremely important because the fact that this delay appears here is the fact that makes that later on this delay appears in the global equations, and we will see. Well, we make a process of linear expansion of this acceleration, the microscopic acceleration, and given that this is linear now, we can say that the average of the acceleration would be the function of the averages. Okay, so the average magnitudes that appear in the equation also are calculated in terms of the macroscopic variables, the density rho and the flux q. Well, q, the flux SV times rho. Okay. And this is the final, after very much work, we end up with this expression, this system of PDEs. I'm sorry, I omitted here equals 0 in this second one. Okay, this is a mistake. And there is a change of variable. This is in terms of the variable S, which is the interspace between vehicles. That is the inverse of the density of vehicles. Okay, so this is meters per vehicle, and the density is vehicles per meter. Okay, so what we have here is that we have a function, specifically the momentum equation, that is depending on tau, on the delay, and this is very important. On the one hand, this allows us to make some kind of linear stability analysis to say, well, when this flow will break up, when waves are gonna start to form because we have reached a limit in this delay. This is doable with also with the standard methods, looking for the eigenvalues of the characteristic equation. I don't know if you remember from differential equation, but this is more or less standard. You can check when this system is not stable and when some waves are starting to be formed in the traffic process. The other one is that this allows us for stochastic analysis too, because and this is the work in progress and is probably the more novel aspect of this study is try to check how when this delay is not constant, is a random process following a specific probability distribution. You have here what is called a random dynamical system, and you can study it. And this is something that we are doing right now. I can't say much more about this because, in fact, I am studying now a lot about this kind of problems. Okay. Finally, I don't know how I am in terms of time. Okay. Okay. So what we have done in parallel to all of this, of course, is to try to carry all these mathematical models also to reality, because at the end of the day we are engineers and we want to see the things. I like to see things and touch the things I am modeling. No? So what I have done in parallel to all of this is to set up a simulation platform to simulate all these traffic processes. To do this, I have relied on NS3. I assume that many of you are aware of NS3 right now. No? NS3, nobody is working with NS3 right now in all the room? So I'm surprised. Well, NS3 is a simulation platform, what is called sometimes Monte Carlo simulation, an event-driven simulation, or discrete time simulation. Okay, and it is built to model telecom systems, and it has implemented inside the libraries many of actual systems that are used in reality. Models for any telecom system now out there, 3G, 4G, 5G. Of course, all the Ethernet families, many things, and up to the IP, all the IP stacks in Unix. You can simulate many things. This is really complex. This is done in C++. They have also some Python extensions, and this is many times used to, if you make an analysis, performance evaluation of a specific system, this is used to build the model, or to model or simulate the model, so that you can check how your model or your analysis is correct or not. Also, to simulate situations that are not that you are not able to analyze because they are too complex. Okay. I can think of many mobile users using different types of traffic, generating different types of traffic, big files, small transactions, moving at the same time, and with a specific coverage of 3G and 4G and 5G different on the areas, and doing roaming between or handovers, sorry, between the different technologies. So this is something that is used extensively in some research, specifically in performance evaluation. And what we have done is to build on top of some mobility models that are already implemented, simple mobility models, because they are also only useful for constant velocities and constant acceleration movements. Well, we have built on top of some object of this library for constant acceleration. We have built all the necessary information to model this kind of models. Okay, so for instance, this has no difference at all between these two graphs, but this has been generated. It's the same graph at the beginning, used generated with MATLAB with the Runge-Kutta numerical integration, and this one is made through simulation with this model, implementing the vehicle as a software entity that reacts with certain rules, that follows the rules that we have given the microscopic model. And you can see there is no difference between the two graphs. The space and the velocity, relative velocity evolution is exactly the same. Okay. Well, this is useful up to a certain point because this is a simple model. But this is also to show you that when the delay is very big, the analytic solution provides negative values for the space, for example. This is not realistic. So in this, the big oscillations here are for the space, and you see that they reach, well, probably you don't see, but I tell you that these are negative values. For the simulation, of course, you can prevent this and make a much more realistic simulation. In terms of what is happening, the analytic model do not take into account that two vehicles will crash one against the other. That consider that they can surpass one another, but this is more realistic. Okay. The point is that when you implement also these microscopic rules and simulate not one vehicle, but let's say 100, 500, 1,000, we have been able to simulate very scenarios with a very high number of vehicles with this microscopic behavior, we end up with the ways that I speak about. This is the representation of the typical situation when you accelerate, if you encounter the block in the road of some congestion, then the congestion dilutes, the vehicles start to accelerate again, they keep up, get more speed, and then again they get another congestion, and well, these are the waves that are formed in a dense traffic situation. Okay, and so we see how you change from the microscopic behavior to the from the microscopic behavior to the macroscopic behavior. And this is done now with this simulator. What we intend to do is, of course, develop some models for the stochastic behavior of the delay, which is a performance evaluation of the telecom system and how this impacts in the traffic. Okay, these are the standards that are now out there. These are the standards, one for the IEEE in terms of mobility control, and these are for the LTE 4G generation. Now there is an evolution. The characteristic of these new systems is that they have a much shorter delay in the communications. Normally, you are going to use broadcast communication between the vehicles because rely on the telecom infrastructure is for all the communications this is not possible. So for sure, these systems will be using what is called in 5G the mode 2 for the broadcast transmission between the different vehicles. Okay. Well, this is the problem that we even made one initial simulation in which just to test how the influence of the density of the traffic would influence in the delay and the delay in the dynamics of the system. So we simulated what happens when the density in the other lane of the road changes abruptly, and how this impacts in the delay and in the waves or in the oscillation that are created in one vehicle that is following the other. This, of course, is when you are relying on self-driving cars or self-driving vehicles. This is probably not realistic right now, and even for small vehicles, it's probably not going to happen. But there will be some floats of trucks, probably, or they are devised for the future, floats of trucks that are more or less self-driven, and this will be also very relevant, how they behave. Okay? And this is for the macroscopic view. Well, this is here we have the delay, here we have the space and velocity variables. This is stable because the delay is still around 2 seconds, but when the delay for any reason grows very much, you start to form and you end up with some here. But this is some simulation we have done, and well, that's all from my side. Again, if you want more details on any part of these works, this is something that is in part some working, or for its most part still work in progress, but I think that many things I can share it if you want. Nothing else from my side. Thank you very much for the attention.
If anybody has any questions, yeah, raise your hand.
Yes, I was interested in the microscopic model, and maybe you said it and I missed it, but how did you get to the approximation with the truncated Taylor and Fourier coefficient? Was it like more analytical or numerical?
No, it's analytical, of course. I guess you mean here, right? here is the linear approximation first of the microscopic equation. This is a,
the first part. Yes.
Here we don't yet. This is a non-linear equation in general, okay? And this is the equation we are parting from in our studies, okay? And it's non-linear. You see here the variables are the s and S prima, the space and the velocity, relative velocities. So this is non-linear, and this is what we linearize here when we have to use this acceleration. Is the same function here. In terms of s and S prima. In this case, we are using more variables, okay? Because in general, the acceleration will use or will be affected also by the derivative of the relative speed and the absolute velocity. But at the end of the day, what you do here is to derivate a with respect to time, which is the derivatives with respect to s and S prima, etc., multiplied by these derivatives, and apply this equation for the linearization. I don't know if you, or maybe I misled you on.
You approximate the solution with the.
But for the macroscopic here, well, the details here. This is a kind of. This is the first one. Sorry, I see now what you're doing. Here is the first one, first approximation to take out the delay. Here the problem we have is that we have the delay here, and then we take out this way. But then what we do, because you start, we'll have here some kind of non-linear equation. You're right. This is a linearization to take out the delay. But here, what you do is this linearization around the equilibrium point S00P. The equilibrium point in terms of space, relative velocity, relative acceleration, and absolute velocity will be a situation in which all the vehicles will have the same inter-vehicle distance, zero relative velocity, zero relative acceleration, they will go with the same, and all go with the same velocity. So if you do this series expansion around the point S00B, you see? And it's with this gradient, of course. Yes, I see. Sorry, I did not interpret correctly your question. Does this answer your question? Okay. Any more questions?
Yeah, I am recently working on this topic, but recently on pedestrian mobility and exchange of messages, banks, and so on. And I was wondering why choosing NS3 on this, because typically, for example, for V2X communications, I know that many people is using artery, and I wonder why didn't you go for that rather than NS3?
I went for this because they have some vehicle models already implemented.
Mm-hmm.
They are simple models in the sense that the mobility is simple. Is
follow the
constant. No, not even follow the leader. What they have implemented is constant velocity and constant acceleration mobility. Follow the leader I have implemented because they didn't have. Okay, so that is one reason. The other one is that in NS3, the main reason, NS3 has implemented most of, well, I can't say all because I don't know, but many protocols, and is quite up to date to many new protocols and mobility protocols.
Does it have the ETSIT stack for 811 BD?
I think, yes, I can check because, well,
because when we were trying to look for that, we didn't find it, at least in artery recently.
I know for 5G models, I think they have.
Mm-hmm.
I think the mobility, this one that is the mode 2 of
the sidling communication.
The broadcast, the sidling mode communication, the mode 2 of sidling. I think that one, and that one is one I was interested. For the IEE, I'm not sure. I don't know. But I have to say that the main reason is that I expected and I knew that for 5G have something implemented, and I wanted at the end of the day, to check all this in a more realistic situation with the mobility model and also with the real communication, with the real or simulated communication on top of that. And that is something that I'm intending to do. And that is why I am using NST.
Yeah, I mean, that would be amazing. I think also that is the lack of the simulations.
Yeah.
Also when we are using them.
Yeah. That's why we are also trying to merge the two dynamics in one, and it's not easy because normally the simulation platforms or the modeling is very focused on one or the other dynamic.
Right? And I have two additional questions.
Maybe it's better to continue. Because I'm not
Okay,
sure if
well, later on if you want, we can.
quite specific for the
Okay.
So we can thank the speaker again. And our speaker, returning to the more classic topic here is in biotech is Marina. She studied health engineering in University of Sevilla, and then she came here to study a master's in University of Autónoma in neuroscience, and now she's pursuing her PhD in ETSIT, in trying to diagnose Parkinson due to the walk of the person with surface electromyography, I believe. I think it sounds really interesting, so the floor is yours.
Thank you. Well, hello everybody. First of all, thank you for coming today. As he has explained very well, I'm Marina. I am doing my PhD on biomedical engineering here in the UVM, but I normally work in a group of the TOPIC. So I'm going to present you what I supposed to become my thesis in not so many years about quantifying the early neuromuscular alterations in Parkinson's disease with surface electromyography. So, well, the presentation will be divided into these contents, and I'm going to begin with a little introduction. So, Parkinson's disease is the second most prevalent neurodegenerative disorder after Alzheimer's disease. In fact, I don't know if here in the room, you know maybe someone with Parkinson or have contact with Parkinson's patient, because it's quite prevalent in our society, and now that the population is becoming elderly, this is increasingly growing. So, well, first of all, what is Parkinson's disease? I have put that like this generic definition with a lot of text, but I want you to retain three main contents. First, neurodegeneration. What is neurodegeneration? It's like a progressive and irreparable neuronal loss in the brain. And which kind of neurons? Well, in Parkinson's disease, there is a death of dopaminergic neurons in the basal ganglia, which is an area of the brain that is in charge of regulating motor signaling and movements. So, well, here we can see like the difference between the healthy basal ganglia and the Parkinson's patient, which has a remarkably loss of these kind of neurons. So this affects to the way that movements are controlled in these kind of patients. Well, normal motor control works like a signal is generated in the brain, and then this motor signal travels along the spinal cord and reach a motor neuron, and in that way the motor neuron activates the muscle fibers, producing movements. But in Parkinson's disease, when this basal ganglia is affected, there is a less movement control, so the movements are not so precise, and also some motor symptoms appear, which are mainly these ones, like bradykinesia, which is slow movements, vocal symptoms, rigidity, tremors, gait disturbance, and well, normally Parkinson's disease is like most known to be a motor, but we have to be careful because it's not only a motor disorder. It has also a lot of non-motor signs like depression, anosmia, which is loss of the sense of smell, gastrointestinal symptoms, sleep disorders. But and also these non-motor symptoms are manifested earlier in the course of the disease. But which is the problem with Parkinson's disease nowadays? First, that as we have already seen, non-motor symptoms are so general that they can be easily misinterpreted. Maybe I go to a clinic and if I have sleep disorder, it's too risky to say, oh, you're going to have Parkinson. We cannot do that. So the clinicians trust more motor symptoms, but which is the problem, that motor symptoms manifest very late in the course of the disease, when more than the 70% of the dopaminergic neurons have already died, so you cannot do anything to stop the progression of the disease at that point. And also that the diagnosis is mainly clinical, which means that it's based on the subjective assessment of clinicians of these motor symptoms. So there is a need to develop objective and qualitative measurements to try to anticipate or to make more objective the diagnosis of this disease. So here is my work. Like inside of motor symptoms, you have gait disturbance, which is the affection of gait. And talking about neuromuscular mechanism that underlies the gait alterations, we have the altered recruitment of motor units, symmetry, and simplification of motor control. I will go into detail later. But gait disturbance is something that is very not remarkable in this kind of patients. And also gait has been widely used to objectively quantify movement disorders, because you can use traditional approaches such as kinetics, kinematics, or spatiotemporal techniques, but also you can use surface electromyography, which is the only technique that allows you to relate motor symptoms that you can see, like gait disturbance, with the underlying neuromuscular mechanism, and also in a non-invasive way, which is also very important. So the aim of my PhD thesis is to try to characterize this muscle activity in Parkinson's patient, to try to find some new objective biomarkers that could anticipate or objectify the diagnostic procedures. So, well, I have the how I can say this? The official scientific questions and hypothesis, but I'm going to explain it like a more relaxed way. So, well, first I want to know which are the neuromuscular mechanisms that are underlying gait. So, my hypothesis is that as Parkinson's disease is caused by a depletion of dopamine, this is going to be affecting the way of the Parkinson's patients work, with an altered recruitment of motor units, asymmetries, and simplification of motor control. Then, are there any muscle activity features that specifically define and distinguish Parkinson's disease from other similar neuromotor disorders? Because non-motor symptoms can be very common between them. So my hypothesis is that the mechanism causing the disease is going to determine, in this case, gait and other neuromuscular mechanisms that underlies them. So there are going to be distinct features between one another. And finally, how those features change across the progression of the disease. And my hypothesis is that gait is going to become worsen as the disease progresses. So the methodology, I have divided it into three main blocks. First, preliminary work, then experimental protocol, and finally, data analysis. So as preliminary work, I have been working on developing a methodology that allows us to do what I have just explained, to relate motor symptoms of, in this case, gait disturbance with the underlying neuromuscular mechanisms. So I have been developing a methodology with other databases that were existing in our lab with other neuromuscular disorders, in order to first develop this methodology and like kind of test and obtain some results, and then compare these results with Parkinson's disease. And these two databases are for the stroke and for spinal cord lesion. Then the experimental protocol involves the recording of a database of Parkinson's patients, in which I'm working right now, also Parkinson's patients and age-matched healthy controls, So this is the setup. We have the Vicon cameras, which are motion capture systems. And the database is going to be multimodal because we are going to use several kind of sensors and in different terrains. The instrumentation is compounded by 17 inertial measurement units of XSense, then 20 reflective markers of Vicon, and also we are going to study 8 muscles of the lower limb. This is the back, the front and the back view. And well, the protocol involved 2 main tasks. First, time up and go, which is a standard clinical test that is used to evaluate this kind of disorders, in which the patient starts sitting down and he has to stand up, walk as fast as possible until 3 meters, turn back and come back and sit down again. And this is sometimes it manifests the walkability like very well, so it is widely used, and also a gait over 4 different terrains. And as I wanted to study the progression of these features across the disease, we are going to do a first-year experiment, then in the second year, and then 3 years after, to see how these features evolve. So these are some videos of our experiments. Here we have the time up and go and the gait over flat terrains. We have all the instrumentation here, and we use a harness as a security thing. And here we have irregular terrains, which is the thing I said, different terrains. We are trying to put patients into extreme conditions to see if these alter the feature that we are obtaining. My hypothesis is that when you are walking into more difficult terrains, your gait ability will be worse. So here we have empty terrain, which is kind of ramps, like an M, that's why it's called like that. Also we have soft terrain with a mat, and also terrasensa, which are brown modules that try to simulate random irregularities. So now, inside all this protocol, my work is focused on surface electromyography. Here is the instrumentation and the muscles we are going to study. And for those that may not know, surface electromyography is just a technique to analyze the electrical signals of muscles produced during contraction in a non-invasive way. So now, once I have all the data recorded and everything, I will analyze it. And I'm going to focus on time frequency domain techniques because, well, EMG is a non-stationarity signal, which means that frequency changes along time. So I think it's very important to study, to have a more complete outlook, to study frequency of these signals in time. So as I stated at the beginning, my hypothesis is that gait disturbance is mainly related to recruitment of motor units, gait asymmetries, and simplification of motor control. And these techniques allow us to see all of that. So, well, the recruitment of motor units is altered in Parkinson's disease and a lot of movement disorders. And well, I'm going to explain it a little bit. This is a motor unit, which is the union of a motor neuron with all the muscle fibers that it innervates. So the recruitment means how many motor units are recruited in a muscle contraction. So, for example, for more precise movements, different motor units are going to be recruited and in different quantities than, for example, in faster movements or more strength. Then gait asymmetries is clearly Parkinson's and a lot of movement disorders are clearly hemiplegic, which means that one hemisphere of the brain is more affected than the other, and this will be related to these gait asymmetries that we can observe. And also simplification of motor control means that the brain is organized to not to send an individual signal to each one of the motor units. They have like some kind of unities or pools that they activate for each movement. So this I believe that is also altered in Parkinson. So the work done until now, I have perform the spectral analysis of a stroke gate. I have used also this three-wavelet transform, which is a mathematical transformation of the signal to obtain time frequency domain representations. And we have recorded 20 Parkinson patients and 20 controls. And the work we are doing now is applying the same methodology of spectral analysis and this three-wavelet transform to the spinal cord lesion database and to Parkinson's disease. To add continuous wavelet transform, which is another mathematical transformation that is more advanced to see if we can find new features and continue recording new Parkinson's and healthy controls. So if everything of these we manage to do that, we will manage to define a set of quantitative features to not only define Parkinson's disease, but also to distinguish it from another neuromotor disorders. Also to describe the change of these features along the progression of the disease and related to the gait condition with these irregular terrains. And also we hope that this could be a tool to assess clinicians in the diagnostic procedures by making the diagnosis more objective. And well, for my part, this is everything. So thank you for your attention. And if you have any questions, I would be glad to answer all of them.
Anybody who has
Thank you for the talk. I was wondering, when you gather those 40 patients, you also consider the age of the patient and the gender in order to be able to see if when you can extract, let's say, the electrical signals, you can discriminate the Parkinson, even though they are from different, let's say, groups.
The thing is that, well, each person in the world is different, so we have a lot of variability. So we have tried to, in the inclusion criteria of our experiment, to make this as homogeneous as possible. Like we have a range of age, a specific rate of the degree, because we have set the degrees of some clinical scales that you have to, you cannot be over those grades, because it would mean that you have a worse state inside of the disease. So we have tried to establish the more uniform set of patients that we could. But yes, when we start analyzing everything, we are going to do like a mix of all of them and see what happens. But yes, in the future, it would be interesting to maybe divide them into female and male, or a range of age, or so yes.
I have a question. Thank you for the talk and the presentation. It was very beautiful. And I wonder if you analyzed any Parkinson patient where the diagnosis is unclear. Like you said in the introduction that sometimes due to subjective criteria from the doctor, they can diagnose or not diagnose Parkinson. If you have tested one of these subjects where they are not sure if he has Parkinson or not, so maybe to test if the protocol can.
Well, the problem with the diagnosis of Parkinson is that it's not only in some cases, it is always subjective. I mean, patients came to the clinic with some reports for the neurologist, and it's also like, it could be Parkinsonism, maybe it is Parkinson. It is never, you cannot say you have Parkinson until maybe you have like this post-mortem diagnosis where you can see if they are amyloid things in the brain and everything. So it is always subjective because it is based on clinical scales, which means that move the leg and the clinician consider that this is stage 1 or 2 or 3. It is always subjective. So all of our patients have subjective diagnosis. So well, in the future, this project aims to use machine learning with all of these modalities of sensor to try to create a tool to support the diagnosis. So yes, all of our patients have subjective diagnosis. So we hope that we can find some signs that may be not noticeable for the human eye, that we can really, with more security, affirm that you have Parkinson or not. And also try to find some prodromic signs, for example, in gaze in this case, that can anticipate the diagnosis. So we're trying to do that, but it's difficult.
Thank you. Thank you for your presentation. When you try to get the electrical signals, are you focusing on any special body parts, or do you believe that there are any body parts which can give more information?
Okay, well, we are only studying lower limb, legs, not lower limb, lower body, yes. Because we are studying gaze, so we're studying leg muscles. But inside leg muscles, I'm normally focusing on tibialis anterior, because the more distal the muscle, the more difficult is like the control of the brain. So I'm normally focusing on tibialis anterior and also triceps uri, which is gastrocnemius and soleus, because it's like where patients have more difficulties. For example, in a stroke, that I have also studied that, they have a common symptom that is foot drop, which is when you cannot do like this and your foot is like drop. And that is because of a spasticity of these muscles. So yes, inside of all leg muscles, these are like more important, as I believe. Also, it would be interesting to study maybe arm, because one of the main symptoms is that you lose this arm swing, that this is normally occur. So maybe it would be interesting to also see some differences in the activation of arms while working.
Similar to the question. So the machines that will estimate the control in Parkinson, these are early stage diagnosis?
No. They are theoretically healthy. Like they have no movement disorders, like they know they can walk normally. No. Well, and I forgot to tell that the experiments are off medication, because normally these patients are taking levodopa and everything. So we try them to be off medication, and the controls we are recording are theoretically healthy of the same age. So we never know, but.
So we consider you have control by your patient.
Yes.
Consider that maybe someone.
Yes, maybe someone later develop Parkinson. We never know. One of the future projects we are thinking of is to also study prodromic patients. We have from the Gregorio Marañón, which are doing this study of distinguish between prodromic and more advanced stages, to study them also with this kind of protocols and compare.
So we close here. If we want a further discussion in any topic there, go here and it's there. So thank you very much.